The following Slinkey Lab 5. The purpose. The purpose of this lab is to analyze a slinky free falling and create a computational model to determine the position of the slinky during the fall by calculating only gravity and then including the tension of the spring. Importance. The momentum principle is utilized to determine the force acting on the slinky, and the momentum principle is used to update the position of the slinky. The physics. So in this lab, we're going to be using the momentum principle, which is F net equals mass times acceleration. That can be rewritten as the velocity final equals velocity initial times delta t times F net divided by mass, which can then be used as P final equals P initial plus the average velocity times change in time. For this lab, the F net will equal 0 while the bottom of the slinky is in static equilibrium. But once the top meets the bottom, the F net no longer equals 0. So then the F net will equal the drag force plus the weight force plus the spring force. The drag force is equal to the air resistance, which is equal to B times the velocity squared times the negative J hat. B is a parameter based on the properties of the object. And the weight force is equal to the gravitational force, which is mass times gravity times the position vector. And then G is the constant, which is 9.8. And then F spring is the spring force, which is going to equal negative K, which is the spring stiffness times the new length minus the initial length. All the forces are affecting the Y component of the velocity and position vector. The analysis. So here we have the tracker. And the tracker gave the initial position of 0, negative 1.840. I tried to find more of the center of the mass than the actual bottom of the slinky. So gravity, the code. So here we basically have all the initial positions. So we have the mass, the ball's initial position, initial velocity, the initial time, the delta t, which I decided to do 0.05, and then the gravity constant, the J hat, because which is only in the Y component because that's all that's going to be affected in this lab. And then for this one we have B equals 0 because there is no drag force for this code. So then the next part of the code is basically using the formulas to calculate the new velocity, which would then be used to calculate the new position. So right here we have the F net only equals the mass times J hat times gravity to get the weight force, and then we have the updating for the velocity and position, and then the rest of it is just to add to the graph and data at the end, and then we just have the arrow scale and the arrows for the gravity. So next we have the code with the gravity, drag force, and spring force. So then again here we just have the initials as before. The only new thing is that we have now a number for B. And then for this lab I inputted an S, which I calculated by just averaging how much the spring would be compressing to the back to the relaxed length during the time period. And then K, I calculated K by setting S equal to 0 and then subtracting that by 1. I just used a general formula to calculate the position graph so that it could apply to almost any spring. So here again we just have the formulas. So we have this up here. So the first while loop is basically going to be for when the ball has no net force acting on it, it is in static equilibrium. So the position and velocity are going to be the same for each time it runs through the loop. And then for the second while loop, that's when we input the new forces. So we have the work force right here, which is of course the mass times gravity, and the times J hat, and the drag is the parameter times the velocity squared times the negative J hat. And then we have the spring force, which is going to equal negative K times S minus 1 times JK. So then we just update those right here, and then we just append those, and then we have the arrows right there. So the results. The computational model with only gravity did not achieve static equilibrium, as you can see, because it just goes straight down. like what happens in real life when dealing with the Slinky. And then the computational model with the three forces were closer to the prediction, but it did not decline as fast in the negative y direction as the real Slinky. So as you can see, it did have the static equilibrium force, but as we started to go down, it did not decrease as much as the actual Slinky. And that's probably just because I used more of a general equation with the -1 instead of using the actual length of the Slinky, because it's just really hard to gauge that with such a large Slinky that I had. Okay, so what does this mean? The reason why the bottom experienced static equilibrium during the free fall was because the top mass and stretch was pulling the bottom into the positive y direction because it wanted to return to its relaxed length, but the gravitational pull was preventing this by pulling in the negative y. So the forces balanced out, and because there was no motion happening to the bottom mass because the velocity was 0, there was also no drag force until there was no longer a spring force because it had returned to its relaxed length. So basically all of that is saying that the F net in static equilibrium equals 0, and then once the top had came down and changed that F net, it began to move. So improvements, what would I do differently? If I was able to do this lab again, I would definitely try to find a Slinkey that was either smaller or metal so that I could find better calculations, and I would also try to just gauge that a little bit better. It definitely has some issues with such a long plastic one because it was sort of more malleable, and it was falling lopsided, and it was just not fitting with the coordinate axis I put on the tracker. So those are the things that I would improve. So thank you for watching.